Hello everyone. So this is the last experiment on the hardware part of your control system laboratory. Name of this experiment is position control with velocity feedback. As I said earlier, in this experiment, we would like to address the trade-off between the controller gain and the overshoot. That is, if we in the earlier experiments, if we increased Kc, overshoot would increase, speed would increase as well. So increase in overshoot is a negative, increase in speed is a positive. If we decreased Kc, overshoot would decrease, which is a positive for us, but speed will also decrease, which is a negative for us. So we are not getting a situation where both of these is improved. That is, overshoot is also low and the speed is also high. In order to achieve that, we use another control, which is another feedback, which is a velocity feedback. So now our block diagram will look like this. R is our input, and we have Kc over here. We have Kp. We have Ki. We have our output. Output is denoted as C. From output, we have our primary feedback. And now the velocity feedback, where the velocity is, we know that before the integrator, we integrate velocity to get output, which is position. So before the integrator, in this position, we have a velocity. Now from this position, we'll introduce a velocity feedback kV. Now, where should we introduce this feedback? If we introduce this feedback to this position, this circle, then what will happen? The Kc will have an effect on the velocity feedback. But we do not want that, because if Kc has the effect, then these both conditions will not be improved, because the trade-off is caused by Kc. So Kc cannot have an effect on the velocity feedback. So we just put it here. Here plus, minus, and we have a velocity feedback here. This is how the system is supposed to work. Now, the thing is, it works like that. The nature of operation is, we will increase Kc to increase the speed, and we'll increase Kv to decrease the overshoot. So Kc will be increased to increase the speed, and Kv will be increased to decrease the overshoot. So as a result, we can control the overshoot we can improve the overshoot using Kv, and we can improve the speed using Kc, which will be working independent of each other. And as a result, we will get better performance in all the respect. Now, uh, now there are certain factors certain equations by which we actually design the value of Kc and Kv. Since there are two variables in here, Kc and Kv, the equation or setting up the value of Kc and Kv are not actually that easy. So the equations that are there are empirical equations that have been devised, and there's a vast explanation and vast derivation of this. I'm not going into this. I'm just going into the expression. You have the expression in lab sheet as well. Kc is equal to pi by Tp whole square, where Tp is the first time of peak, 1 by 1 minus zeta square. If you remember, zeta is actually our damping constant, 1 by Kp Ki omega c. Kp is the plant gain, Ki is the integrator gain, omega c is the break frequency. So this is constant, and zeta and Tb will actually depend on Kc and Kv. Now Kv is equal to 2 zeta root over Kc Ki divided by Kp omega c minus 1 by Kp. So these are the formulas. We do not need to learn the derivation of this. We do not even have to memorize this formula. We have to use this formula in order to design our system. We'll be using these formulas later. Before that, we'll have to take a look at certain things. What are the things that we will be taking a look at? Firstly, we know the speed rise of TR is proportional to 1 by omega d. If TR is proportional to 1 by omega d, we have known that omega d is equal to 1 by root over k omega c minus omega c square by 4. We can find this equation of omega d if you look at the equation. If we can find this equation of omega d if you look at lab sheet of experiment 4. Now from this we get TR is proportional to 1 by root k. When can we write that TR is proportional to 1 by root k? That is an important factor. The important factor over here is, let's not use this equation. Let's rather use a different equation to understand it better. So we know that uh, if we don't use this expression, we have another expression which is root over k c k p k I omega c 1 minus theta square. So you will remember this expression of omega d more clearly because I have taught you in class in the lecture. So here kp is constant, ki constant, omega c is constant, variable is kc and variable is zeta. So we can write rise time is proportional to 1 by root over kc only when zeta is constant. So we cannot derive or come to this understanding as if zeta is not constant. If the zeta constant means overshoot constant. For a constant value of overshoot, our rise time will be proportional to 1 by root over kc. So the greater the value of kc, the smaller will be the value of rise time. And this proportionality is something that we will be experimenting with, and we'll be finding out in our this experiment, that is in our experiment number 5. Now let us now move to our simulation setup. So let us move to the lab sheet at first and see how it will be set up. So CA06PE08, so we load CA06PE08. We look back at here. Signal is step, level is 10%, offset is 0, wait is 10 milliseconds. So what we do is, we do not need our drive signal, we turn it off. We do not need anything except the input and output, so we turn all the other things off. So we have input and we have output. Now, okay, sorry, output is our position and not velocity. This is the position purposes. So we have our inputs and outputs, and we see there is a very high value of gain. There is a very high value of overshoot. Now, what we'll first do is, we'll first set Kc is equal to 2.5, which is already set, and we will increase the value of Kv bit by bit so that the value of the overshoot is really small. So what we do, we increase the value of Kv, overshoot is decreasing, we increase it further, we increase it further. So there is no overshoot. We don't want this position to occur. So we decrease it. We want to keep a very small amount of overshoot. Very small but not zero. So suppose 2.5 for our, if our KV is 2.5, we have a very small overshoot. Take a very careful look at this overshoot. One thing you can see is that you can actually, by increasing KV, you are able to decrease the overshoot without affecting the time response. Time response is ever so slightly affected, not as much affected as it would have been in case if velocity feedback was not there. So let us look very carefully at the overshoot. This overshoot will be important. Now, what we'd see is what we'd see is if kV was equal to 0, if kV was off, in the right hand side top corner, you'll see that there is a lot of jerking involved. That is the the machine itself, the motor that we're using, the servo motor, that will reach a constant point. That will reach a constant point. That is, it will hold a constant position in both the directions, but there will be a lot of jerking involved in it. Now, if we increase the value of kV, suppose we are increasing it to 2.5, you can again look at the top right corner that the jerking is very less, but still that position is being held. So as a result, we can see that the speed of reaching the final position is being improved by Kc, and the jerking or the overshoot is being reduced with Kv. Now let us move back to our experiment. So what we do is we increase the kV value in such a way that there is a very small amount of overshoot. Then we write this value of kV over here and also over here. Then we measure the rise time. What is the rise time? We freeze it. We take the time, and the point where this output intersects the input, this is the rise time. So rise time is 0.32. And our value is kV is 2.5. So kc is equal to 2.5, kv is equal to 2.5, tr is equal to 0.32. Let us look at it again. Yes, tr is equal to 0.32. Now we start again. Now we change the kc to 5. You'll readily see that overshoot has increased since Kc has increased, and time response has also increased. That is, the system has become fast. Now we increase Kv. So what we want is we want to have the similar level of overshoot that we had seen in our earlier part. So if I remember it correct, the overshoot kind of looked like this as in that case also. So our kV here is 4. So we go on to our second set of data. Kc is 5, kV is 4, and our rise time would be, let's freeze it. So T rise time would be 0.22. So we write it, rise time is 0.22. 0.22. Again, it is one thing you need to observe is why we are actually uh, keeping this overshoot constant. We are keeping this overshoot constant because we can derive this relationship between rise time and Kc only if the overshoot is constant. If the overshoot is not constant, we cannot express it in this way. Now, next thing is we want to make Kc is equal to 10. To do that, we increase Kc to 10, 6, 7, 8, 9, 10. Then we start it. The overshoot has risen again. We increase Kv. So the overshoot kind of, if we decrease it a bit, so the overshoot is kind of what it was in the earlier case. So again, we freeze it. After freezing it, we see the rise time. The value of kV is 5.8 and the rise time is 0.16. So we note it down. This is 10, this is 5.8, this is 0.16. Now the last line over here is expected rise time. Now expected TR, we will not find expected rise time for 2.5, but see, Kc is being increased 2 times. So what should TR be? TR should be should decrease by 1 by root 2 you should increase by 1 by root 2 times. That is, this TR should be 1 by root 2 into 0.32, because since kc is increased 2 times, kr should decrease by root 2 times, that is 1 by root 2 into 0.32. So 0.32 divided by root 2. So our expected rise time is 0.226. So 0.226. So our expected rise time and the actual calculated rise time, they are basically the same. Again, from this to this, the value of Kc is again doubling. So as a result, this should be root of 0.22 divided by root 2. So what is 0.22 divided by root 2? 0.22 divided by root 2 is 0.155, which is very close to 16. So this phenomena, that TR is proportional to 1 by root k when zeta is constant, is proved by the data table. One thing you need to be very careful about, that this is true only if zeta is constant. That is why we're doing is we are seeing the overshoot, and we are trying to keep the overshoot constant in all the measurements. We are not trying to keep the overshoot zero, but we are trying to keep the overshoot very small and constant in all the measurements. Now, at the last stage, the the actual motive of this control system hardware laboratory is that we'll try to design an entire control system. What do I mean by that? Let us recap at the course that we are having. At first in experiment 1 and 2, we modeled a plan. Model a plan. In experiment 3, we observed feedback. In experiment 4, we observed a second order system. In experiment 5, we observed how we can improve the second order system using the velocity feedback. Now, after all these things, we have a sufficient knowledge of actually designing a second order system. That is the last and final motive of our experiment. That is, design a position control system. When we are given this problem, we will be stated some design parameters. For example, if you just look at this part of your report, wait, let me see. Okay, uh, this should be somewhere in the theory, but I can find somewhere in the lab report, but I can find it at this moment. But that's not necessary. That won't be a problem. Okay, this is here, design exercise. Determine the gain and velocity feedback, that is Kc and Kv, for overshoot of 10% and first peak of 300 milliseconds. So we are told to design a system which will have percent overshoot of 10% and Tp is equal to 300 milliseconds. So if we are given a very random motor and we are told to design this system, what do you do first? We first try to understand what are the parameters of motor. We try to model the motor. How can we model the motor? We can find the Kp, we can find the Ki, and we can find the time constant tau. And from this process, we'll be finding the break frequency as well. So from experiment 1 and 2, our task would be modeling the motor. So in your case, you will not have to model the motor, because we have already done that. We have already modeled the servo motor in experiment 1 and 2 with a definite set of Kp, Ki, tau and omega c. In the next stage, after we have modeled the motor, we know how the motor works and what are the constants related to the motor and how we can define the motor. Then we have to design the controller. Experiment 3 and 4 state what are the effects that controller has on the system. For example, experiment 4 told us that if we increase the Kc, the speed will increase, but overshoot will increase. Experiment 3 told us if we increase the controller gain, then the error will be less. So these are the factors or the basic theories that we learned from experiment 3 and 4. Then in experiment 5, we have a formula. Formula says that Kc is equal to pi by Tp square, 1 by 1 minus theta square, 1 by Kpki omega c. 1 by kpk omega c. We know the Tp given in the system. We know zeta from the overshoot. We know Kp, Ki from and omega c from experiment 1. So we can readily determine Kc. And after determining Kc, we determine Kv. How can we determine Kv? We can determine Kv from the formula 2 zeta root over Kc Ki divided by Kp omega c minus 1 by Kp. We can determine Kv by this equation. And after determining this equation, what do? We put these equations in here and here, Kc and Kv. By putting this equation here, we will find the output system and we'll observe that the output will have a definite, will have a desirable value, that is overshoot of 10% and peak time of 300 milliseconds. So what we learned from this course is, from this course we have learned that if we are given any set of motor or any system, we don't know what the system is, and we are given a device with which we can provide the input and see the output, then if a problem statement says that design a position control system that can do this, we can do that. We can at first model the plan, then we can design the controllers and get the desired output. Now, since it is a problematic thing that you are not actually doing this design part of the experiment with the hardware, but in case of that, I'm just telling you what would happen. You're designing for percentage overshoot of 10% and TP for 300 milliseconds. So your output should look like, suppose the output should have looked like something like this. But when you actually put the value of kV and kc, what would happen in the actual system? Output will look like this. You're designing for an underdamped system, but the output will become overdamped. Why would that be? That is because in case of actual machinery, there is always the formula that we have learned is not, it's theoretical formula. It is not taking into consideration the different types of frictions and wear and tear of the motor. The apparatus that we use in the library is very old. They have gone through a lot of wear and tear and friction and stuff. As a result, what happens is the parameters that we are measuring, these parameters do not give the result that we expect. That is the output. Even if we make the output, design this thing as an underdamped system, that can become an overdamped system. This is the reason why we don't actually make a critically damped system. If we design a critically damped system within a very short period of time, even within days or months, the system will become overdamped system, and gradually damping will increase. Damping will not decrease. It will keep on increasing. So speed performance would decrease by a great margin. So what do? We create a range of overshoot that is acceptable to us. Whenever we are designing, suppose a lift, we suppose we introduce an overshoot of 10%, that much jerking is acceptable to the people riding the lift. If the jerking is 30%, it would be very scary and will not be acceptable. But 10% is acceptable. That is, it is not a problematic thing for us if it is if it jerks 10%, but it will give a good speed response. So over time, the performance will decay, and even if performance decays, it will ultimately reach critically damped position, and at a very later time, it will reach over damped position. So the lift will be operating at our desirable performance for a longer period of time. So in general, whatever we design, we keep a scope of a little bit of overshoot, and we actually design an under-damped system. We do not actually design a critically damped system unless the problem statement specifically states it, or the stability is very, very, very important. Otherwise, we do not design critically damped system. So the course or the hardware part of it is over. So from this part, if you understood it enough, if you are given a motor and a system from which you can give an input and output, I hope you'll be able to design a position control system using the overshoot and uh, time parameters. So if you can design such a system using the software, I think your control system course or the laboratory part is successful. That's all for this course, and maybe I'll see you in another course. Thank you so much.